Hello, and welcome to the second video of the FP3 chapter, Further Coordinate Systems. On the screen, as usual, is a starter question. Pause the video now if you've got time and give this one a go. To save you a bit of time, here is the formula for the equation of the normal to an ellipse. Here we go. The ellipse C has an equation x squared over 5 squared. So straight away that tells us the value of A, plus y squared over 3 squared tells us the value of B is equal to 1. The line L in red on the diagram is normal to the ellipse at point P. We have the tangent here as well, but that's not necessary, it's just there to show you the normal. And that passes through the point Q, which is also on the ellipse, and where the line cuts the y-axis. Find the exact coordinates of the point R, where L cuts the positive x-axis. So what we're going to do here, we're going to need, first of all, to find the coordinates of Q, which is quite easy, because at this point the x value is 0. And of course we've got 2 points there where the x value is 0, but we need the positive one. So if we put x equals 0 into our Cartesian equation, we get 0 plus y squared over 9 equals 1. So that gives us y is equal to plus or minus 3. And as we said, q is the positive, so the coordinates of q are 0, 3. Okay, the coordinates of q, that is on the line and on the ellipse. Because it's on the line as well, it must also satisfy the equation of the line. Now I've put this on just to save time going through it, but if you hadn't memorized that, then you could very easily, so long as you've understood the previous video, you could very easily get that again by using the parametric equations x equals 5 cosine t, where t is the parameter, y is equal to 3 sine t, and going through the process that we talked about in the previous video. Parametric differentiation, find the gradient of the tangent, use m1, m2 equals minus 1 to find the gradient of the normal, put it into the line equation. Doing all of that with the numbers will give you basically the same equation as I've got here in white, except you'll have the numbers, where a we know is 5, so you'll have 5x sine t minus 3y cosine t, and here you'll have a 16 cosine t sine t. So whether you've memorized this and used this, or whether you've used the parametric equations from here to then differentiate and find it fresh, you should get to this point for the equation of L. So using the coordinates here, because we know that Q is also on the line L, we can substitute these coordinates into this equation in order to find the only thing we don't know, the parameter t. So if x is 0 and y is 3, then we get a nice 0 coming out here, minus 9 cosine t is equal to 16 cosine t sine t. Rearrange and solve for t, gives us cosine t 16 sine t plus 9 equals 0. So of course either cosine t is 0 or sine t is equal to minus 9 over 16. Now you've got a few different answers here. We could go on to find the value of t. That would give us 4 different answers. But we don't actually need the value of t. We need the value of sine t and cosine t. And because we can relate sine and cosine together, once we've found one of them, we can find the other. But we need to be careful to know which one is appropriate for the line that we've got on the diagram. Because here cosine t equals 0, that would give us this line. And if you notice, that is still normal to the ellipse, and it still goes through Q. That's why this is one of the solutions, but it's obviously not the line that we want, because we know our line comes out and crosses the positive x-axis, and this line does not. There's a second answer for t in here as well, which would correspond to this line going down this direction, normal here, still crossing through Q, but again we can clearly see that's not the one we want. And from the sine t we can't actually identify which of those two lines it is, because sine t is negative in this quadrant and in this quadrant, but we can fix it to be this one in this quadrant with p here instead of over here by forcing our cosine to be positive, if you remember the cast idea, where in this quadrant here, if sine is negative and cosine is positive, then we've got this point, whereas if sine was negative and we chose the cosine to be negative as well, it would be this point here, and it would be this line, which we don't want. So I can choose my cosine to be positive in order to fix this in the correct place, and I can do that by doing cosine squared t is equal to 1 minus sine squared t, and when I square root, I take the positive root. The alternative to doing it this way and thinking about the cast diagram is to actually go ahead and find the value of t, use the value that gives you this quadrant, and then put that back into cosine, making sure you're keeping the exact value on your calculator, and it will give you the correct value of cosine for this quadrant, because you'll have fixed this quadrant in the value of t. In order to keep my values exact, I'm going to have to do this as fractions and make sure my calculator doesn't get too enthusiastic about changing it into a decimal. And if you do that on the calculator and you square root it and you take the positive root, we get 5 root 7 over 16. And again, I've taken the positive root specifically because I know it's this line with p in this quadrant, not the line over here where p would be in this quadrant, which would mean I would have to have a negative. So I'm choosing that to coincide with the p here, and that gives me everything I need to know about this line. T in here, or more to the point, sine t and cosine t in here, I know what these two values are. I know everything else, I just don't know x and y, but for the point r, we can fix that y must equal 0. So I put y is equal to 0 in here, sine t and cosine t in here and here, and I can find out my value of x. And that should be our final answer. So we've got 5 times x times sine t, which is minus 9 over 16, minus 3 times y, which is 0, so all of that is 0, is equal to 16 times cosine t, 5 root 7 over 16, times sine t, minus 9 over 16. And we can see that once you get rid of that 0, that cancels with that, 16 cancels there, and 5 on both sides cancel, and we get the surprisingly simple root 7 answer for x. So that is the starter question that reviews a lot of what we did last time in a slightly more problem-solving question. So in this video we're going to do similar things with tangents and normals, but before we do that we're going to look at the equations of hyperbolas, because it is hyperbolas or hyperbolas that we're going to focus on in this video for the tangents and normals later. Very similar idea, but we need to know what the equation of a hyperbola is. And it is this. Very similar to the ellipse, but instead of a plus we have a minus. And obviously you've got to be a little bit more careful here because the minus must go with the y squared term. Whereas with the ellipse, if you switched them around, obviously that wouldn't have made any difference. Parametric equations for a hyperbola. Very similar again, we're going to use the a with the x term and the b with the y term, but in order to choose trigonometric functions that will make this correct, we need a something squared minus something squared equals 1. So we can't use sine and cosine anymore, because sine squared minus cosine squared, or cosine squared minus sine squared, does not equal 1. And we have two options here. We have either cosh and sinh, because if you substitute this in, a squared cosh squared, the a squared will cancel out. Here, b squared sine squared, the b squared will cancel out, and hopefully you've either done this and come back to this chapter, or you can take it on faith that cosh squared minus sine squared is equal to 1. And sometimes I teach this chapter later in the module so that the cosh and the sine are a little bit more familiar. But if you're doing this chapter before looking too far into the hyperbolic functions, don't worry, there's an alternative, and that is sec and tan, because similarly sec squared t minus tan squared t is also equal to 1. So both of these work as parametric equations for a hyperbola. I tend to use cosh and sine because either as you know or as you will find out later, the derivative of these is quite easy, because the derivative of cosh is equal to sine, and the derivative of sine is equal to cosh. No negatives, very easy. So I prefer these ones. However, I'm aware that if you're doing this chapter second, you might not have done these things. Whereas if you've done the third chapter or the fourth chapter before this chapter, that should be very familiar to you. There's nothing else in this chapter except for these three things, however, so if you're happy with that, you're happy to accept that, then you can still do everything from here on without any other sine and cosh knowledge. And the alternative is still here, if you don't mind differentiating sec and tan. Sketching the graph, get rid of that. To sketch the graph, we need some key points. The first key point is what happens when y equals 0. And if y is equal to 0, you can see that goes away. The a squared comes up, square root both sides, and we get x is equal to plus or minus a. So these are our intercepts on the x-axis. Then you would very naturally ask what happens when x equals 0. But when x equals 0, you end up with y squared equals minus b squared. And obviously if you square this number and you square this number, you can't have something that satisfies this, because you'll have a positive here equals a negative here, because you'll always get a positive out of the b squared. So that cannot happen, which tells you that a hyperbola never crosses the y-axis, unless you're doing some sort of rotation of the plane. But in general, you will find that there is no y-intercept. So we need a little bit more to help us sketch this. And we can look at the idea of x tending to infinity. What happens when x gets really, really big? And if x gets really, really big, this term is huge, and in order to make the difference equal to 1, then this term also needs to get bigger and bigger and bigger. So the bigger this is, in order to make this equal to 1, the bigger this must be. And as that gets really, really, really big, the 1 becomes almost negligible, and you can approximate the x squared term and the y squared term must be approximately equal if they get big enough. So we can rearrange that, and we get asymptotic lines at y is equal to plus or minus b over ax. So these are lines that the graph will never quite reach. The graph will not be on these lines at any point, but it will get closer and closer and closer to these lines. And that gives you enough to sketch the graph, and it should look something like this. So when you're sketching these, make sure you have the x-intercept number here and here. Put in some dotted or dashed lines for the asymptotes. Label what they are, and sketch as best you can a curve that gets closer to the asymptotes and goes through those intercepts. And that will be fine. So here's an example. Sketch the hyperbola given by the equation this. Similar to the ellipse, my first step is to get a 1 on the right hand side. So I have x squared over 4 minus y squared over 9 is equal to 1. Then I can identify that a is 2, b is 3, and the asymptotes happen at y is equal to 3 over 2 x, and this is a plus or minus. So a sketch here, a is at 2 and minus 2. Then we've got our asymptotes a little bit steeper than 1. And a little bit steeper than minus 1. So here we've got 3 over 2x, and here we've got minus 3 over 2x. And then my curve just needs to fit in here, reasonably symmetrical. It curves down, gets closer to this one, closer to this one. And there we go. Should just add these in for completeness. And we've sketched our graph with the information we need. So here's a table. I'm not going to go through each of these individually, but pause the video now if you want to have a go at filling this in. And in 3 seconds I will press it and the answers will come up. There we go. So if you did that and you got them right, well done. If anything went wrong, have another look and see what happened. Find the equation of the tangent to the hyperbola with the equation this at the point this. Okay, we've done the basic equation of hyperbolas. Now we're doing much the same thing as we did with ellipses, just with a slightly different equation, a minus here instead of a plus. But all of the ideas are the same. To find the equation of a tangent, we need to differentiate this either implicitly or using parametric equations. Then use that gradient at the point given to find the gradient of the tangent, or if you need to find the normal, do m1, m2 equals minus 1. Then put that gradient into y minus y1 equals mx minus x1 with the points given, and you'll have your equation. So that is what I'm going to do, and I'm going to do implicit differentiation. So we get 2x over 9 minus 2y over 4 dy by dx equals 0. We can cancel some of these out. So we rearrange this to get dy by dx, 4x over 9y. And I want the equation of the tangent, so that's the gradient. Now using the point I've been given, I know that x is 6 and y is 2 root 3. So we can cancel a little bit more here, and that will give us 4 over 3 root 3, or if you like to rationalize your denominators, 4 root 3 over 9. So this is the gradient of the tangent at this point. Now we can do y minus y1, which is 2 root 3, is equal to the gradient times x minus x1, which is 6. And that is the equation of our tangent. And you could rearrange that and make it look a little bit nicer, but the question here does not specify a format, so I'm going to leave it there. Okay, again, very similar to the ellipses video, we can prove a general equation of a tangent, or the general equation of a normal, by doing all of this with the general equation starting point, or the general parametric equations. And we're going to prove that the equation of a tangent is this. Again, it's all the same process. This time I will use parametric differentiation because I've got the parametric equations here already for me. So dx by dt, and you might have noticed I'm using t rather than theta. That's fairly common, don't let that put you off. That gives us a sin t. Dy by dt is equal to b cos t, and remember with the hyperbolic functions there's no negative here. So dy by dx is equal to b cos t over a sin t. And of course, if you wanted the equation of the normal, you could turn that upside down, put a negative in front, and that would be good to go. But we want a tangent here. So now I've got y minus y1, the general point b sin t, is equal to b cos t over a sin t from our gradient times x minus x1, the x coordinate a cos t of the point P. Now it's just rearranging. Multiply everything by a sin t. We get a y sin t minus ab sin squared t is equal to bx cos t by expanding out the brackets as well, minus ab cos squared t. And to put it in the format they want, I'm going to leave ay sin t here, bx cos t here, and I'm going to move ab cos squared t onto the left. Factorize out the ab. So we have ab cos squared t, and there's also an ab minus with their sin squared t, and that has to equal bx cos t. Now if you've done this already in a previous chapter, you'll know it, otherwise I put it on the screen near the beginning of the video, that cos squared t minus sin squared t is equal to 1. So that gives us our result directly. And there we go. I've said it a few times now, I'll say it one more time. Very similar to the ellipses, there are 3 results here. We've only done one, we did this one. But we did the proof for this one and this one in the ellipse video, and it's basically the same, except there's a negative in here, so they come out slightly different. I have a negative here, for example. And again, I wouldn't necessarily recommend memorizing these two, because they're quite long and complicated, but this one might be useful. Of course, if memorizing comes easy to you, then as we saw at the very beginning of this video, it could save you a bit of time if you knew these off by heart. Of course, knowing them off by heart doesn't help you if the question is asking you to prove them. So make sure you know how to do it from first principles as well. That should be enough for you to practice questions from exercise 2b about hyperbolas and sketching them, and from 2e about finding the equations of tangents and normals. And maybe I'll see you in the next video.